So we start with this one, that is optical isomerism. All of you know this is what is you have to be. This is our main topic today, optical isomerism. But it is not that only you know the definition. There are lots of things which you have to, and configurations and other things. And many misconceptions you have got. You have to get rid of those misconceptions. That is what misconception you have got. You will slowly realize about that. So we start with definition as usual. It's optical activity. First of all, to understand optical isomerism, you must know what is optical activity. What is optical activity? Plane polarized light. This is what we have to use. We use plane polarized to study optical activity. So when plane polarized, it pass through the solution of some substances. The direction of plane polarized either rotated towards right or towards left, then the substance is known to be optically active. So we know that this is optically active substance. If it rotates the plane polarized light either right or left. Now, if it is optically active substance, if the substance is optically active, this is what you see here, optically active, then this substance will have two varieties, means two isomers. One of which will rotate the plane polarized light towards right and is known as dextrorotatory or simply D or plus isomer. And other one rotates the plane polarized light towards left and is known as levorotatory or L or minus isomer. So this is, there is no, there is nothing to know much about this one. Already you know it. All right, I can go ahead. So one is what you know as dextrorotatory and levorotatory. Now the question is, what type of molecule will exhibit optical isomerism? This is the main question that we have to answer. And for that, what is required? For any optically active compound which show optical activity, what will have? Asymmetry in the molecule. That means the molecule has to be asymmetric. There are lots of things which you have to be there to show whether it is going to be optically active or not. The first criteria that is required, the important criteria is that it has to be asymmetric, or the term used is asymmetry and the chirality. That is, only those compounds are found to show optical activity as the optical isomerism, which are asymmetric, which do not have any point or plane or line of symmetry, also known as chiral system. The word chiral is used in this case. If the substance is asymmetric, is going to be, I think you know what is asymmetric system. You can structurally asymmetric. This is what we have to emphasize. Now let us see. Now, if it is optically active, we know that it is going to be either dextrorotatory or levorotatory. If it is dextrorotatory, it rotates the plane polarized light towards right. Or if it is levo, it rotates towards left. But to what extent it is rotating? It is rotating the plane polarized light to what extent? Means how many degrees? So for that one, some definition has to be fixed, and that one is given by a physical constant called specific rotation. Now, how do we define specific rotation? For any optically active compound, specific rotation is a physical constant defined as the angle of rotation of plane polarized light observed, which when passed through a solution of the substance in a cell of length 1 decimeter. Be careful, here it is 1 decimeter. 1 decimeter means what? 10 centimeter. Having a concentration of 1 gram per ml and measured at 25 degrees centigrade. So that rotation, whatever rotation we get here, that is called your specific rotation. Now you can schematically show it here. So this is the plane polarized light. This is the solution which is kept here. having a concentration. We not necessary that we have to always measure, make this concentration. We make a concentration of C gram per ml, and this is one L decimeter. Suppose length is L. We have to calculate it in terms of 1 decimeter. Now, this would have been the straight path, but it got rotated by this, the plane polarized light came this direction. So the angle made is alpha, suppose. So this is the alpha observed. This can be measured by an instrument called, what is the instrument used to measure this specific rotation? Can anybody tell it? What is the instrument that is used? Hello?
Sir, polarimeter.
Polarimeter, yes, good. So it is polarimeter, right? So this equation can be given by this. Specific rotation is alpha, suppose. This is alpha observed by L in by C. Okay. Now, you take down a problem here and give me the answer later on. You take down, just all of you note down this problem. Note down the problem. 28 milligram of an optically active compound. 28 milligram of an optically active compound dissolved in 1 cc ethanol solution in 10 centimeter long polarimeter cell. 10 centimeter long polarimeter cell gave optical rotation minus 4.35 degree at 20 degrees Celsius. Find specific rotation of the compound. Find specific rotation of the compound. CONPD. Achha, M is not here. Find the specific rotation of the compound. So this one you will calculate and give me the answer. Not now. Just keep it. Note it down. I'm going to next page. Is it okay?
Yes,
okay.
sir.
All right. So I'm going next. Now come. So what we have seen, what type of molecule exhibit optical isomerism? The compound which is going to be chiral, asymmetric. We are dealing with organic molecules. Okay, organic molecules. For organic molecules, what is that? The simplest organic molecules which are found to be optically active are molecules with an asymmetric carbon. What is meant by asymmetric carbon? The carbon bonded to carbon bonded asymmetric carbon. That means for we know that optical isomerism will be shown by molecule which are asymmetric. But for organic molecule which are an asymmetric molecule, what happened? Udit Nath, why you have given a sketch like this here? Don't give any scratch in your screen.
Hello, sir. Sorry, sir. My phone has dropped my phone.
No, you should not use such device. Okay. Asymmetric carbon, the carbon bonded to 4 different atoms and groups, also known as chiral carbon. So this is the term, already you know it. So here everything that we are doing, it is all that you know. Okay, let us see. Now what is that? Such molecule will have 2 spatial arrangements which are non-superimposable to one another structurally and non-superimposable mirror image structures and are known as enantiomers. Now let us see. You see here, Do you see this molecule? Okay, this is a tetrahedral carbon with 4 different groups. One is blue, red, this is pink and green. Okay, so this is an asymmetric molecule. Now, if it is an asymmetric molecule, it will have its mirror image structure. Mirror image structure means what? If I put one mirror here, another structure that comes up. These two structures will not be superimposable one another. That means this red, the other structure, when I take, the red will, all 4 will not fall in each other. That means green and green, red and red, blue and blue, and pink will not fall on each other. Okay, the second molecule I take here. This is, now you find here. Now, is there any difference in their structure? Just see. Are they same or different?
Same.
Huh?
Same,
Same, sir.
same.
Same.
Sir,
So same when you see it from a distance, right? But you see, are they not mirror image structures? Just see. If I put it here, they are mirror image structures or not? Imagine
Yes,
a
yes, sir. Yes, sir. Yes, sir.
mirror image structures. And you say that they are same. But according to this version, what we find, they are not same. They are different structures. How they different? If they are same, if I just superimpose, they should fall on each other. Red should fall on red, blue should fall on blue. Now let me just try to match them. Green is green, red is red. But now, what happens to this? This pink and is falling on blue, and blue is falling on pink of the other. In no way we can make it. So what are they same now?
No, sir.
No, sir.
So they are
No, sir.
different.
No, sir.
So they are different. So these two different optical isomers. If one of them rotate the plane polarized right, the other will rotate towards left. Now, can you tell which one will rotate towards right and which one will rotate towards left? Can you tell? Okay, because this is not a real molecule. So when we come to real molecule, that time I'll ask you again. Now you see, they are not going to be. They are two different structures. Now, they are also configurational isomers. I said configuration. What is the difference between configurational and conformational isomers? Configurational isomers can be changed to one another by breaking up the bond. Okay, let us try. One molecule I take it here, which was different from the other one. Yes or no? Which was just mirror image of the other.
Sir.
yes, sir.
Now,
Yes, sir.
if I want to make that one same as the other one, I must break the bond. So I break these two bonds and change their positions. I break them, I change their positions. That means I again reset them. So I have broken and then again made it. Now it should become same as this one. Now I will find. Now I just see. Now you see. This blue, green, pink, red. Are they not getting on one another?
Yes, sir.
Yes,
So,
sir.
Yes,
so
sir.
what is the conclusion then? That means these two isomers can be changed only by breaking of the bond. But if they are mirror image structures, I can make again they are different original one. I just break and make them. Now this is mirror image structures, and these two mirror image structures are not superimposable. That means they are different. They are different. You find them, they are different, and they are two optical isomers. One of them will be dextro and another one will be levo. Okay, now we come to, and these are called enantiomers. So these terms should be very careful. You should be careful about these terms. They are called enantiomers. Now, enantiomers gave optically active compound. Sorry, of a given optically active compound will have all their physical and chemical properties same except specific rotation. So this is a term that you have to. Now let us take one example. So already I have shown this one, two wedge structures to a structure A, B, C, D, and this is mirror image of the other. They are not superimposable. Fisher projection, they are not also not superimposable. When we handle Fisher projection, that time we have to be careful. We cannot rotate in any direction we like. We'll see that one later on. Let us take now one complete example. So let us take this molecule, say lactic acid. Lactic acid is an important example here. Lactic acid is important example. This is a chiral center. This carbon is chiral. This is CH3, COH, one is H and another O. So the two structures that we'll have will be like this one. If we put one mirror here, so this will be mirror image structure. So this structure is different from this structure. So they are called enantiomers of lactic acid. Enantiomer of lactic acid. Okay, now can you tell me which one is going to be dextrorotatory and which one will be levorotatory? Can you tell by looking at the structure? Hello.
OH group in the right hand side will be dextrorotatory.
OH group on the right hand side will be dextrorotatory. Who told you? Is it written in any book?
No, sir.
Huh?
No, sir.
Then why you are telling like that?
I'm just guessing.
You are guessing. So here, please make it a point, no guesswork. By looking at the structure, you cannot tell which is going to be dextro and levo. Keep it in your mind. Now, this structure, when we take this one structure, we have to take it to polarimeter and see whether it is dextro or levo. It is an experimental observation. Remember that OH is coming on the right hand side, so that is going to be dextro, and if it is on the left hand side, it is going to be levo. No. That one you cannot tell. So let us stop that argument now. But anyway, these are two enantiomers, you know that one. Now what is found? The physical properties are all same except their specific rotation. So let us see this. For lactic acid, we'll be having one is plus lactic acid, another is minus lactic acid. Its melting point is 18, specific rotation is, density 1.248, specific rotation is 2.24 degree plus, because it is dextro. So it is plus lactic acid, another will be minus lactic acid. And what is this plus minus lactic acid? It is a mixture of, equimolecular mixture of plus lactic acid and minus lactic acid. Its specific rotation will become 0. This is called, what it is called? This mixture is known as what? Already you know it. So I'm just asking. That is called?
Racemic mixture.
Racemic mixture. So that will be racemic lactic acid. Now let us see this term. So plus minus lactic acid is an equimolecular mixture of plus lactic acid and minus lactic acid, and they are known as racemic mixture of lactic acid, and will be optically inactive. It will become, the specific rotation will become 0. But here, because it is a mixture, we can separate them. We can separate them, and And that separation process is called resolution. So this racemic mixture is an equimolecular mixture of enantiomers. So any enantiomers, what are enantiomers? Enantiomers means mirror image structures. Given optically active compound, such mixtures are optically inactive and show specific rotation 0 degree. Okay. Now, separation of enantiomers of a mixture of any optically active compound is known as resolution of racemic mixture. So here also this is the term you should be acquainted with, called resolution of racemic mixture. And their physical and chemical properties can be, there are physical and chemical methods by which we can do this separation. So that separate, there are methods, you can read it from there, from books. So this is, now, if I quickly come, we cannot finish it today. If we quickly come to, suppose with one chiral center, we have got two enantiomers, we got two optical isomers. Now, if we have more than one, suppose we have two chiral center, then how many optical isomers will be there? So molecule with two chiral centers. A molecule with two chiral center, what we'll be having, will have four different configurations. That means four different arrangement of atoms and groups around these two chiral centers. So suppose C is bonded to ABC and this and DEF, and shown as below. This one, let us see it. Suppose this is two chiral center. One is this is one, and this is another. So this is bonded to A, B, C, and this whole group, and this is bonded to D, E, F, and this whole group, because it has to be bonded. So all are different. In such case, we'll be having four structures, four possible structures. And these structures we are writing, they are Fischer projection structures. So what is this 1 and 2? 1 and 2 are the mirror image of this one. So there is mirror, they are mirror image structures. And three structures, we just change one of them. Suppose I change this one we keep it as it is, and this one we just change it. That means change by breaking the bond. That means when I write F here, D here, here it was D this side, right hand side, and F left hand side. When I change them, that means I have broken the bond and then changed it, not by just shifting, not by rotating this bond. So we get another structure 3, and its mirror image structure. So this way. So these are total 4. You can try anyway. It is not more than 4. But what is their relationship like? These 4 configurations using Fischer projection. Let us see now. And if we have n different, suppose then if we have n different numbers, we'll be having 2 to the power n number of optical isomers. So this is a point that you should remember. There will be n different number, but for constitutionally asymmetric molecules. If the molecule becomes symmetric, again there will be some problem. We'll be discussing that point later on. Later on means here only, after in the next slide. But we'll stop here after we finish this slide. So what is here? Let us see the relationship. 1 and 2 and 3 and 4 they are mirror image structures. Yes or no? 1 and 2 are mirror image structures. 3 and 4 are mirror image structures. So these pairs, that means 1 and 2 are enantiomers. 3 and 4 are another pair of enantiomers. But what about this structure 1 and 3, or 2 and 3, or 2 and 4, or 1 and 4 are not mirror image structures. Say 1 and 3. They are not mirror image structures, but they are optical isomers of the same compound. So what will happen here? What is their name? These are called the same compound, and these pairs are known as, I think you know it, diastereomers. They are called diastereomers. That means diastereomers are are mirror image, are optical isomers of the same compound which are not mirror image structures. Even the cis-trans isomers that we get here in other cases, suppose cis and trans that we got, they are actually diastereomers because they are not mirror image structures. In that case, of course, they are not optically active. In this case, they are optically active. All of them are optically active, and they are not mirror image structures. I think you got that point. But once they are diastereomers, in case of enantiomers, what we find, their physical properties are going to be same. But in case of diastereomers of 1 and 3, their physical properties are going to be different. So that point you have to note down. So in case of, say, geometrical isomers also, symmetric cis and trans, their physical properties are different. So I think we will stop here for today because what is the next one? Let me see. If it is okay, no, this one will require some more explanation. So with this, we'll end up here today's class. I will forward your this video. Let me see how it comes. If it is all right, I'll send it to you, and you will go through the videos. And that time you can, because but this all these things that we have done today is your things that you already done it. But I am taking it here because just to make your foundation good, so to understand that other things, other topics that we'll be taking later on in the session. And as I say, you go for, I mean, we'll meet only after Bihu, vacation. So after that, we will increase one more class. We'll increase one more class because this class, one class will not be sufficient, maybe. So I end this meeting. So all the best, happy Bihu to all of you, and we meet after Bihu. And anything, any problem you face, you can write me there in my WhatsApp, or you can communicate otherwise also. All right, you can call me also, no problem. Do you want to say, anybody want to say anything? Hello? Hello? Do you want to say anything? Do you want to say anything? Yes or no?
No, sir.
Okay then. So
No,
all the
sir.
bye. So we end our class here today.